long now have I been here? How long will I stay? Got a little more work to do before I'm on my way. Tying all of my loose and still got debt to pay. Picking up the pieces before I'm on my way. Before I'm on my way. Before I'm on my way. Before I get there, before I show up. How long now have I been here? How long will I stay? Got a little more work to do before I'm on my way. Tying all of my loose and still got debt to pay. Picking up the pieces before I'm on my way. Before I'm on my way. Before I'm on my way. Before I get there, before I show up. How long will I stay? Got a little more work to do before I'm on my way. Tying all of my loose and still got debt to pay. Picking up the pieces before I'm on my way. Before I'm on my way. Before I'm on my way. Before I get there, before I show up. How long will I stay? Got a little more work to do before I'm on my way. Tying all of my loose and still got debt to pay. Picking up the pieces before I'm on my way. Before I'm on my way. Before I'm on my way. Before I get there, before I show up. How long will I stay? Got a little more work to do before I'm on my way. Tying all of my loose and still got debt to pay. Picking up the pieces before I'm on my way. Before I'm on my way. Before I'm on my way.
All right. So, it's really important being a software programmer. You need to know what kind of hardware that we are dealing with. So previously, we have learned that, a lot of stuff that we thought to be trivial, that if I can use well, if theoretically, smart, elegant operation like bitwise operation, it should be faster, but it's actually pretty counterintuitive that some of the code that looks not as space efficient is going to be more efficient on modern processor hardware. You might think that if I do additional stuff, then it make your code slower. But since we have a branch predictor, we know that now if you get your data sorted, it's going to be faster. And now we are going to talk about more about modern hardware design in a way that you're going to know that in microprocessors today, we do more than you can ever imagine to make your code more efficient. So maybe a lot of stuff that you think I should have done in software programming is now unnecessary. But before we talk about that, there are still important things that we need to talk about. Remind you. So first of all, the whole purpose that we are trying to optimize our program, the whole purpose of modifying our design is because we want to achieve the goal that modern pipeline processors, in theory, we can generate the outcome of an instruction every cycle. However, it's not in many cases, it's not possible because 3 different types of pipeline hazards. For example, structural hazards that you may have resource conflicts that cannot support simultaneous execution of instructions in a pipeline. Or you have control hazards, which means that the program counter can be changed by branch instructions in a pipeline. Or you have data dependencies that you just have to wait, right? So those are the reasons that we cannot achieving our ultimate goal, CPI equal to 1 for each pipeline. So to address the data hazard issue, we talk about data forwarding, which basically we try to create wires that can forward results from other ALUs or memory units whenever it's possible to do so. However, it's still pretty limited if we have code that creates data dependency that cannot be resolved by those forwarding hardware. So today we are going to continue our discussion on how can we make performance better and ultimately achieving the goal of better CPI. So before we get there, here is where we are. Rocket Team really rocks in the last lecture, so that's why you seem like all the teams are pretty close now. And before we talk about the main content of the lecture today, I do have a question that I want to have you guys think about and discuss in group. So, we are close to the time that we have midterm election. I just want to ask you a question. If you are the governor, what would you do to make DMV more efficient? Well, I guess this is probably the most question that people feel the most empathetic about. So we already see people raise their hands. So Anthony, do you have any idea?
Yeah, if I was a governor, I would make it so each city has their own DMV, and there'll also be
Okay, each city has a lot of DMV, okay? What
dedicated
else?
members, more members. So that's kind of parallel
Members.
hardware, and then we're
Okay.
boosting that up. And we can also try have more formal DMV training, so people will be more efficient. Like and the line,
Mm,
and
okay,
I guess that's it.
keep going.
Oh,
Okay.
we keep going.
No, because your voice is cut up. So
Oh,
yeah, so you say you want more DMVs. You want well-trained staff, maybe more staff.
yeah.
Okay. How about each DMV?
For each DMV.
Yeah, you want more staffs, right? So, well, so maybe here is we go, right? We need more windows, right? We need more steps and maybe more DMVs, right? So more DMVs is more like a multi-core processor, I would say, right? But more windows, more steps is regarding for each DMV, we want to equip more. Correct?
Correct.
Okay. Any other thoughts? Any other creative idea? Okay, right. So everyone agree that, if we want to make DMV great again, right, we probably need more staff, more windows, right? So we have been talking about pipeline, right? And in the last lecture, we have been talking about, if we can only fetch one instruction at a cycle, the optimal CPI of a pipeline could achieve is just one, right? But are you satisfied with that, right? So if I only have this amount of instructions to process, then probably fine. But in reality is that the demand of computation is really, really high nowadays. So if your processor can always only produce an outcome of one instruction, it's very limited. So today we are going to talk about a few things that would make our CPI go below one and try to squeeze as much as out performance as possible. And then I'm going to show you what are the modern processor look like, so that in the next week, when we talk about how to optimize your code, then you have a better idea, why am I optimizing my code like this? Or why shouldn't I spend so much time doing this? So the big question we have now is CPI equal to one the limitation, right? So for each single pipeline, right, it's indeed a case, right? So previously we have been talking about the swap code, but one of the problems that I do find in a swap code, it's a good example to show you that, sometimes fancy instructions doesn't help, but a fancy programming style doesn't help. But today, with this example, I just want to show you that, with a more realistic code example that we would interface with every day. So the last time when we have the swap example, it's only a set of instructions mainly for move, right? But most of the time, you also want to do some arithmetic. So today we are going to use another code. This is probably the sum from an array, which a lot of time we do, right? And for this pieces of a code, you can see that we do have the move instruction, we do have the arithmetic instruction, one for counting the sum and the other for increment the address in the array and compare for the loop condition and branch, right? So this is a more representative and fruitful example that we can use. So if you have, well, this code is somewhat optimized already, but if you look at the code, right, it's already a pretty compact representation. But with our pipeline, it still give you a cycle stall because the second instruction here, it depends on ECX, right? So if I have a smart compiler, if I know this is my pipeline looks like, a very trivial optimization that we could do is another thing that we could do is that, well, we can flip the order of add Q and add L. So in this way, there's no stall here, right? So because you put another instruction, reorder this add L instruction, put it down, and that this happened earlier, right? So on the positive side, right, this one won't affect the correctness of your code, and this add Q instruction is for sure being executed. So a golden theory of compiler optimization is that for a compiler, it can only optimize on static instructions, which means that I cannot predict how many times I'm going to execute this iteration, especially if this is a variable, which I don't know what the exact number is, right? So unless this is a constant number that I can know, like for example, 4 times, twice, or 16 times, then I can potentially unroll. But most of the time, if this is a variable that I cannot unroll, right? So if that's the case, then what will happen here is that I can only optimize on this basic block. And from this basic block, what I observe is that, well, this 2 instruction, they could be reordered. And for this particular pipeline, it's possible that I can reduce reduce 1 cycle delay, right? And however, another thing that you might also feel is that, you know, remember the pipeline, remember the processor we draw, right? We have many ALUs, right? So for example, we have many functional units. We have ALU, we have branch, we have memory, right? And sometimes you might think, well, at this moment, right, I am only doing things on memory. The ALU is not used at all. So if there is a way that I can utilize the ALU, I can potentially further improve my throughput. Agree, right? So if that's the case, right, a lot of things could happen earlier to make my performance better. So it's pretty similar to the idea that we have in the DMV, right? So right now you are thinking, you can imagine the processor is like the DMV. And what happened in this DMV is that every time we only allow one customer to be served by any window of the DMV. So everyone is now sitting on a chair, and only one, even though I have 20 windows, only one out of this 20 windows is now working. So that's what's happening right now, right? So if I want to improve the performance of this DMV, right, maybe I should find a way to make multiple windows to work together, right? So this is what we are going to do today is that we have an idea called superscalar. Let's see what a superscalar DMV looks like. So the idea of superscalar is this, right? Since we have many functional units now, but the issue is that, well, we have only one unit that is available. If we can only fetch one instruction per cycle, first of all, there's only one instruction entering the pipeline at any time, right? And if each cycle I have only one instruction come in, and my pipeline has to has no additional storage for more instruction, if my pipeline has no capability of decoding multiple instructions at the same time, right? It's impossible for us to to have multiple functional units working, right? So it's like in your DMV, right? Thinking about your experience in DMV, right? Like there's a door and people line up in front of the door, and there's one reception, right? And this reception is pretty much like the people, the attendee at the reception is pretty much like the decode unit, right? And the decode unit, but typically the decode unit is pretty fast. However, you can imagine now you have a slow decode unit. It's as slow as any other 1 in the window. So it turns out what happened is that the attendee at the reception is really slow in a way that, well, they would ask, what are you going to do? Like Zootopia, right? What are you doing today? And then every time when you try to do stuff, well, and it takes a while for that attendee to figure that out. And then finally someone in a window went out, and she can well, that person can finally can get that things done, right? So that's decode, right? And after decode, right, you can finally decide a functional unit, or say we can put an instruction into execution, which is called issue, right? So issue means that we can, how many instructions we can put into execution at any cycle. So superscalar means that we want to have the processor to have ability of fetching, decode, and put multiple instructions into execution at each cycle. So that's the basic idea of superscalar. With superscalar, we introduced 2 new terms. One is the fetch width. It means how many instructions can the processor fetch and decode at each cycle. And the second thing regarding superscalar is that how many instructions can the processor put into this execution each cycle. So that's superscalar. So with superscalar, what would happen is this is the original processor we have with data forwarding support. And now, see, the change is not that much, right? We just change the fetch unit, decode unit to make it wider by fetching more instructions, decode more instruction, and the ability to put more instruction into execution at any time. So that's the idea of superscalar. So if I assume my processor can fetch and issue 2 instructions at any cycle, for the code that we have in the previous slide, it could be executed like this, right? So this is already the optimized version. And for the first cycle, I can fetch 2 instructions. And then in the second cycle, I can decode these 2 instructions and fetch another 2. And in the third cycle, which is the time that I can issue instructions, then remember our processor has an ALU, has a branch unit, has a memory unit, right? So memory unit is free, ALU is free, and we are able to fetch issue 2 instructions at the same time. So we can actually put 1 instruction in the memory, 1 instruction in the execution stage without any problem, right? So then these 2 instructions, they can be executed together, which fulfill our goal that right now I'm fully utilize this ALU, right? However, if you keep going, right, you will figure out that, well, maybe the performance gain is still limited in a way that, well, I have my third instruction coming in. However, unfortunately, because the ECX value is not ready yet, so this one has to wait. And this compare instruction, although the RDI is already ready, but in the execution stage. However, because this instruction is behind the addl instruction, so I still cannot have this instruction put into execution. So both of them has to stall at the decode stage. Finally, the next cycle, this instruction finished the memory operation. So the first instruction got its ECX. So this instruction can be in execution stage. However, for this compare instruction, because right now we only have 1 ALU, so this compare instruction cannot be executed, and it has to be stalled at the execution cycle. And because this one is stored at the execution cycle, and also I think there's another thing that is wrong here is that this one is depending on this one. So it has to wait for another cycle, right? So turns out that the performance gain is very limited, even though my superscalar processor are now able to issue 2 instructions. However, you can hear a few things here, right? If I can further improve the performance, for example, if I can make this compare happen before this one, and in fact, doing this won't affect the correctness of your code, right? But however, it's not trivial for the compiler to assume this because the compiler has no idea if your pipeline is better for this or that. And the other thing is that from the compiler's perspective, this one is also has another dependency on @q, right? So it's hard to tell which one is more beneficial. Only the hardware knows. So and one more thing, right? If another way to look at the potential gain of performance is that if we can loop, if the pieces of the code is going to loop many times and assume we have a perfect branch predictor, right? Remember that in the last lecture, in the lecture, right? We were talking about we are able to make the branch predictor accurate. So you can assume our predictor is pretty reliable at this point, right? So if we drew the pipeline diagram like that, right? Then you will figure out that, you know, for this compare instruction, right? There is no reason why we cannot execute it, right? And if you keep going, right? Another thing that you might find is that for this move instruction, like memory instruction, they are pretty time consuming. However, at this point, right, like memory unit is free, and I already have my RDI value ready. So this instruction, in theory, if I have a way to make it execute earlier, then I can potentially get more performance, right? So in fact, currently, with superscalar hardware and just compiler optimization, we are pretty limited in a certain way that for the compiler, we can only optimize this group of 5 instructions without looking into more instructions here. And the other thing is that the compiler optimization is very limited by hardware changes. So if your hardware changes, the same compiler optimization may not be that helpful, right? However, if you think about, in fact, what really make the hardware, so some of you ask about what the dash mean in a diagram. So do you remember that what we mentioned earlier is that we have to make sure that all the instructions go through the same number of stages in a pipeline. However, some of the operation, they are really short. So I use the dash, meaning that the instruction is still in the pipeline, but instruction is not doing anything. All right. So so keep going on regarding the limitation of compiler optimizations. If the hardware changes, the same compiler optimization may not be that helpful. And the other thing is that the compiler can only see those static instructions within basic block, and they cannot take opportunities from dynamic instructions. So here's our thought, right? If you think about what do you actually need to execute an instruction, is that whenever I know what instruction want me to do, right? Or whenever everything is ready, right? All the dependencies are solved, and I have a targeted functional unit available. Why not have me execute it, right? So it's pretty much like the DMV. Whenever we figure out what kind of business you want to deal with DMV, whenever you have all the documents ready, you have all the forms filled, whenever there is still a window open for you, why can't you go ahead and get your stuff done, right? That's the ultimate idea. How can we make the DMV more efficient? And same thing for the processor. why do we have to care about the order of the program? Why can't we just execute the instruction whenever the instruction is decoded, whenever the instruction has no data dependency, whenever there is a free target functional unit available for the instruction? So here's the thing. We make the processor available for dynamic instruction scheduling regardless the compiled order of your binary. And this is called out of order execution with dynamic instruction scheduling. So today we are going to look how we achieve that. So as we mentioned, right, instruction without dependency, instructions or say with instruction with data dependency all resolved could be executed, right? So in theory, that implies that if two instructions, they don't have data dependencies at any cycle, they should be able to be executed in parallel, right? So how to figure that out? The easiest way to figure that out is to draw the data dependency graph among instructions. So this is the code we have in the sum of array example. And for the first two instructions, the target address of move L is ECX, and add Q is depending on RDI as the input and generates an output of RDI. However, because the first instruction is only using RDI as the source, so in fact, the outcome of add Q is not depending on the outcome of instruction 1. So these two instructions, they don't have any dependency. And for instruction 3, it depends on ECX and EAX and generate output on EAX. And ECX is coming from the first instruction. So the third instruction indeed have a dependency with the first instruction. For the fourth instruction, its input is RDX and RDI. And the last one who would generate the RDI that this instruction would need would be on the second instruction. So the fourth instruction has a dependency with the second instruction. For the fifth instruction, it depends on the outcome of fourth instruction. So there is also a data dependency. However, the fifth instruction itself is not generating any outcome except for changing the PC. So there will be control dependency on 5, but not data dependency on 5. Now, looking at the sixth instruction, it's depending on the value of RDI, which is generated by the second instruction. So 6 is also depending on 2. Now, for the seventh instruction, it's depending on the latest RDI. So the seventh instruction is also depending on 2. And the eighth instruction is depending on the fresh value of ECX generated from the third instruction, well, from the first instruction, well, sorry, the sixth instruction, and also the EAX value from the third instruction. So that's why we have both arrows pointing to instruction 8, which means that instruction 8 can only be executed after 3 and 6 finish. And for the ninth instruction, it's depending on the RDI and the RDX from, the RDX is a value that's never modified. So it's depending on the RDI from 6. Oh, sorry, 7 here, right? So, and for the 10th instruction, again, depending on the outcome of 9. So this is the data dependency graph for this 10th instruction. So in theory, like for 6, 4, and 7, they should be able to be executed together once 2 is resolved, because 6, 4, 7, they are not depending on each other. Like for 5 and 9, they do not depend on each other. So they could be executed together once the dependency are all resolved. And same thing for 3 and 6. They should be able to execute with together with each other without affecting the correctness if things they do not depend on each other. However, now assume that we have a perfect predictor. Can we really reorder instructions as we would like it to be? All right, looks like everyone has sent in the answer. So I have sent the question to the chat. So why don't we go discuss within groups? All right, let's wrap up in 15 minutes. 5, 4, 3, 2, 1. Time is up. Okay, so this question seems to be really interesting in a way that after discussion, I still see a very diverse answer. So can I have some of the group share your discussion context? Because I think it would be really helpful for all of us to figure out where are the blind spots we have. All right, if no one wants to raise their hand, then I would probably try to pick one group randomly. Oh no, Rocket Team. So who is the representative today? So last time it was Vincent. But Vincent, do you still want to give it a shot today?
I mean, I can try to walk through it, but I don't.
Sure.
I don't
Thank
really.
you. I love you.
I actually am very not sure on this question.
Well, that's fine because I think that's the important thing.
To be honest, I just guessed on this question. I just put A because I'm.
Mhm.
It doesn't seem like 1 and 2 would affect the correctness of the.
Okay, so maybe we can go through each one, right? So
Yeah.
for 1 and 2, first of all, they do not, well, in the data dependency graph, if we put them in this order, right? They actually do not depending on each other.
Right.
But what if I flip their order now? What would happen?
Oh. Oh, right. Because actually you can't do that. You can't do that
Right, you
because
cannot
then,
do that
yeah, because the
because
source would RDI would be used later.
yeah, so
okay,
your
right.
output is actually the source of this guy, right? So
Right.
this is not going to be correct, even
Okay.
though they do not depending on each other.
Right.
Now, looking at 3 and 4, right? 3 and 4, they also do not depend on each other.
Right.
But if we, so are we able to reorder them?
I think so.
Right. So for this too, right? There is nothing wrong. Nothing would be wrong if you reorder them, right?
Right.
So, and they do not depending on each other as well, right?
Right.
So this is actually the correct answer. Now, looking at 3 and 6. So 3 and 6, again, see on the data flow graph, data dependency graph, it's pretty similar to the relationship with 4. But are we able to reorder 3 and 6?
No, because 6 is writing to ECX and 3 uses ECX as a source. So can't do that.
Right. Okay. So this cannot be, right? And
Right.
4 and 7, right? 4 and 7, there's no data dependency, right? But if we flip the order of 4 and 7, what would happen?
Same thing.
Right? Your RDI would be overwritten.
Yes.
Right? So how about 6 and 7?
6 and 7. Same concept again, RDI.
Same concept again, right? For 6 and 7, for 6 and 7, right? If you reorder them, it's like reordering 1 and 2, right? So this won't work.
Right.
Okay, so here we go, right? So it's kind of and thanks, well, Nathaniel, question.
Yes, Professor. So for this type of question, we should look at the diagram and the code, right?
So
like we can
yes,
determine based on the diagram on.
So yeah, you should. It's kind of interesting, right? You should look at the diagram and the code. And for the diagram, right? If there is indeed an arrow, you know you definitely cannot reorder them.
Oh, okay. All right. I think I got it. And then for the code, you cannot reorder them if they have like dependency before words, like the 3 and 6.
And yeah, before I do mention that 3 and 6, they do not have dependency, right? But now you
Okay.
see, if you reorder them, it's going to be problematic.
Okay,
Right.
I got it. Thank you so
Right.
much.
So here's the thing, right? And the reason is because, well, although for those instructions that we said is problematic, they don't have real dependency, or they don't have the real dependency on this data flow graph. However, as you can hear, because we have limited number of registers and we have to reuse those registers again and again. So we have false dependencies at the end. Turns out that a lot of instructions, if I try to write a register, if I try to write a register value after an instruction, well, so now I have two more types of dependencies that would put constraints on how the capability of reordering instructions. So this instruction, we don't call them true dependencies because in fact, there is no real data dependency on them. However, if we have the case called write after read, means that a later instruction try to overwrite a register value that an earlier instruction tried to read, then the value that an earlier instruction depending on would be gone. So turns out you cannot reorder them. So we have seen this in this sequence of code like 1 and 2, like 6 and 2, like 6 and 3. Because for 1 and 2, if you try to change the value of RDI, 1 is not going to be correct. And for 6 and 2, if you reorder them, right? One of them is not going, the instruction number 6 is not going to get the right. Well, actually, I think for 6 and 2 is true dependency, right? So this is not. And sorry, this is not. And for 6 and 3, right, it's also, you know what? I think this slide is out of date. I didn't save the right result. Okay, so let's look at each one. So for 6 and 2, it's true dependency because there is an error on this. And okay, again, right, what is write after read? A later instruction overwrites the source of an earlier one. So here for 2 and 1 is definitely the case. And for the third instruction, it's not yet, right? But for the fourth instruction, it's also not generating an outcome. So the next time we are going to see an instruction generating an outcome like this one is probably when the time okay, so for 6 and 3, right? 6 is generating a different ECX. So if you try to move this instruction with 3, even though they do not depend on each other, but this one is overriding ECX. So 6 and 3 is definitely a case of write after read. And now for instruction 7, it's overriding RDI. So if you try to reorder 7 and 4, it's going to affect the correctness, right? So 7 and 4. And also for the 8th instruction is overriding EAX. So if you try to reorder this instruction, okay, so this one has true dependency. So look at 9. It's also overriding RDI. So if you try to reorder this instruction with instruction 6, for example, right? So 9 and 6, it's going to be problematic, right? So those are, so 2 and 1, 6 and 3, 7 and 4, 9 and 6, we cannot reorder them because of this right after read dependency. And for right after write, it's the case where a later instruction overrides the output of an earlier one. So for example, if you try to move 6 and 1, or well, 6 and 1 is probably not. If you try to say, let me see. Output dependency. So if you try to EAX RDI, Okay, so it's kind of interesting, huh? So here for this 6 instruction, if I have an updated value of RDI, and if I try to reorder it with the first instruction, it's going to make the output of an early one being vanished, right? So those are the example why we cannot like reorder this instruction, even though there's no real dependency among them. So these are false dependencies that shouldn't be limiting our result of execution, right? So in fact, there is a way to resolve this kind of false dependency, as I just mentioned, right? The main source of this dependency is just because these instructions, they reuse the same register. However, if I rewrite my code like this, so for example, now I put the output, so now I slightly change my instruction set a little bit, like each instruction can accept at most like 3 arguments. One is the source 1, the second is the source 2, and this is the destination, right? And if I can make an additional destination somewhere else, then you can check now, right? There is no false dependencies at all, right? So for example, originally we say for 3 and 6, we cannot reorder them because of the dependency. But now looking at this 3 and 6, if I give its output a different register value to store, you can see it's effectively the same, right? Because for the RDI is now, I put the RDI value in T0, and if I forward this T0 value to move L, and I put the move L output instead of in ECX, but a different location, then turns out the move L has no false dependencies with the instruction 3 at all. And you might say, well, it's still depending on T0, right? But remember, it's indeed 2 and 6 is indeed a true dependency, right? But in this way, you can see by using additional registers, we will be able to get rid of the false dependency between 3 and 6. So the key here is, if our scheduling is constrained by those false dependency, and the solution is actually we should use as more registers as possible to store a new outcome and that later instruction depending on the outcome of these other registers. However, compiler optimizations cannot do this because compiler optimizations are limited by the registers an instruction set architecture provides. So for example, x86 only has 16 registers available. And even for RISC-V, we only have 32 registers available. So here we come, the hardware solution called register renaming and speculative execution, which exists in every modern hardware to address the demand of dynamic instruction scheduling. And here is the way how it works. So as we mentioned, the what really constrains our scheduling is the available registers for instructions to use. So our idea here is we decouple the architectural registers, which the compilers and programmers can see. So we just see another layer of virtualization. So you have virtual memories, you have, and now we also make registers virtual. So your code running on virtual registers, and when your codes are in execution, the register renaming hardware would dynamically remap your architectural register to a physical register. And whenever there is a new output, we use a new physical register to store it. And in this pipeline, we will have a new stage called renaming stage, which allocate a physical register for the output of a decoded instruction. And also, we want to have the capability of scheduling instructions across the branch. However, sometimes this is dangerous because, again, although the hardware can predict the future, however, this prediction is not 100% accurate. So there may be chances that your instructions may not be really the one that we want. So if we have to execute instructions across the branch, this is called, we need something called reorder buffer that allow us to temporarily store the outcome of this on the instructions that after an undetermined branch, so that if we found that the branch mispredicted, we are still able to recover the results from the reorder buffer. So that's the basic idea. However, at this point, you only need to know that there is something called speculative execution. The processor has the capability to use the predicted instruction and allow the predicted instruction to execute without affecting the correctness of your code. And remember, in compiler, it cannot do any prediction because it's dangerous to do so, and the compiler might need more overhead to recover incorrectly predicted branch. So the compiler is seldom doing anything speculative. So here's the superscalar processor. And if we want to support register renaming, then the processor would be more complicated, look like this. We now have a register renaming logic, perform the virtual register to physical register update. And also, as we mentioned, we want to make sure that if our prediction is incorrect, we can still recover from the error state. So that's why we have another thing called reorder buffer. So this is the new hardware we have. And let's look at the register renaming in motion. And because we also know that the first two cycles, they are boring because we just instruction fetch and decode. So let's start from the third cycle. So in the third cycle, we rename the first two instructions because right now we are assuming that our processor have the capability of rename and execute two instructions at the same time. So at this point, we rename two instructions. And remember, the idea of register renaming is that whenever we have a new output, we give it a new register to store its output. So now for this instruction, it's actually being rewritten as, so this is actually going to be RDI T2, right? So the first instruction, it generates an output called ECX. And the physical register for the ECX is now saying that we have this physical register. So let's say P1. So for the P1, it's in use and it's not valid because the value is not generated yet. So any instruction depending on P1 at this point, we know the value is not valid, so the instruction cannot be executed. But for P2, is the output for the second instruction, which is RDI. So we put it in P2. So that's what the register renaming basically has to do, just to rewrite this instructions output to a different one. And now for the next cycle, Well, this is the time we can issue this first two instructions. And as we mentioned, we can issue at most two instructions at the same time. And the memory unit is free, the ALU is free. So put them both into execution. And in the meantime, we are trying to rename the other two instructions. So for instruction 3, we have the EAX value is still from the original input. However, the output, we are overriding the EAX. So in our mapping table now, we know the up-to-date EAX would be in a new register called P3. And for the compare instruction, right, we see there is an RDI, and we go to the lookup table, we find the RDI is now in P2. So we write this to be P2. And remember, for compare queue, it modifies the flag, but not the register value. So at this point, I just skip the flag. And for instruction 4, whenever the P2 is ready, it should be ready to execute. And now for the next cycle, you can imagine for P2, right? If you have perfect data forwarding, it should be able to be used by the fourth instruction. So let's see what happens, right? So now indeed, right? Because we have the P2 ready. So anyone who depends on P2 can be put into execution. So that's why now the fourth instruction, which originally had to stall for one more cycle, can now put into execution. And for the add L instruction, it's still depending on P3, which is not generated yet. So we have to stall this instruction. But in the meantime, we can rename two other instructions. And at this stage, you can assume that we have an instruction queue. So the renamed instruction can be queued without blocking other ones. And for the fifth and the sixth instruction, we can do the same thing in renaming them. And 5 is not generating any output, but 6 is. So for the sixth instruction, we put a new output to P4 register, which also update the table saying that if you want the up-to-date ECX value, you should go to P4. And in the next cycle, right? Let's see. In the next cycle, we are expecting to decode 7 and 8. And for 7, it references RDI. And RDI is in P2, which is already ready, right? So, but in the meantime, you also know that 7 instruction would generate another value to update RDI. So what would happen in the next cycle is that the RDI would be updated to P5. But for the add queue instruction, there is no reason why it cannot be executed whenever we have execution unit available for it. And in the meantime, for the third instruction, because that's also the cycle that the memory instruction finishes execution, so we can put the third instruction into execution. And at this time, the 4 is already done its execution. So you are actually flip the order of the execution of 3 and 4 in your pipeline. And now you might wonder, okay, at this point, right, I should be able to have this instruction in execution, but because my memory unit is actually free. However, we do have the capability that each time we can only put 2 instructions into execution. So the issue with is now setting constraints on issuing the 6th instruction. Otherwise, you should be able to issue 6. So we have to, 6 is now has to wait, not because of the capability of functional units availability, but the issue with of your processor. So this is some kind of structural hazard. And in the next cycle, you can imagine we can definitely put this instruction into execution. And in the meantime, as we mentioned, right, the 7th instruction is able to be executed anytime because now no one is preventing it from being executed. So we have both instructions into execution. And if you keep drawing the pipeline diagram, you will figure out that we are able to keep reordering these 2 instructions and generate a result. And another thing that is amazing is that except for this cycle of stalls, right? After a certain point, you will figure out that for this pieces of code, the CPI would be equal to 0.5, which is the perfect CPI that we can get from superscalar. So as you can see here, we are able to extract the full power of superscalar processor with the capability of outer order execution hardware. So this is the mechanism most processors are now using to fully utilize the functional units that they have. And you might feel that, well, if I want to solve this problem, do I always have to draw the pipeline diagram? And the answer is no. You can actually use another way to figure that out. That's called data flow graph analysis. And again, right, the data dependency is what really determines the order of execution at this point. So you can actually use data flow graph analysis. So this is the pipeline that we have, right? Assume that execute ALU instruction has only one cycle, branch one cycle, memory instruction 2 cycles, right? And in the first cycle, we are going to have 2 instructions being fetched, and let's fast forward to the third cycle. So right now, assuming that we are at the register renaming stage and we are about to issue instructions. So now, if I look at these 2 instructions, then I know they don't have dependency. So you just put them into execution, right? And there's only 2 instructions and they do not conflict on the functional unit. Now, for the third instruction and fourth instruction is coming in the next cycle. But if you look at their dependency, the third instruction is depending on the outcome of the first instruction, which takes 2 cycles. So the third instruction definitely cannot be executed right now. But the fourth instruction is only depending on 2, which is the result is available at this point. So 4 could be executed right now, but for the 3, you have to wait for 1 more cycles. And in the next cycle, yes, we are ready to execute 3. However, we also got 5 and 6. And is anyone in 5 and 6 could be executed? And the answer is yes, we can definitely put 5. But for 6, even though everything that 6 needs at this point is ready, because 6 only depending on 2. However, our issue with is only 2. So 6 has to wait for 1 more cycle. Now, in the next cycle, 7 and 7 is depending on 2 only. So 7 can definitely be executed. And it's also not conflicting with the functional units that 6 is using. So feel very safe to execute both of them. And for 8, it's depending on the outcome of 6. So it cannot be executed at this time. So Nathaniel asking why 6 should delay for 1 level is because we have only 2 issue with at this time. So you can at most put 2 instructions into execution. So, and we already have 3 and 5 in execution right now, so you cannot have 6. So for 8, it's depending on 6, so you have to wait. And for 9 and 10, 9 is depending on 7 only. So since 7 finished, you can actually execute 9 at this point. And looking at 10, it's depending on 9. So you can only execute 9, 10 at this point. And if you keep drawing the data flow dependency graph, you will figure out that this is what the overall flow of execution looks like. And you can see that for these pieces of a code, right? If you keep executing it, the CPI would be, you can always find 2 instructions into execution after a certain point. So for this pieces of a code with out of order execution, we are able to make the CPI equal to 0.5. So now using the same mechanism, this question I know is difficult, so you can take more time. But for linked list, a lot of us like this because the algorithm teacher told you is more space efficient. Can we somewhat see For the same pipeline we have in the previous question example, how many cycles it takes for us to have all instructions into execution? All right, it looks like 80% of you already have an answer, which is pretty fast. So let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, although I do see you guys have an answer, but it's not consistent with each other. So why don't we go into discussion? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. All right. So after discussion, more of you are leaning toward the answer of B. So I would like to hear from you. Any group would like to try? All right, let's see which group. Oh, okay, it's the blue team. Let me see who is in blue. I guess Anthony, Chris, Nathaniel, Salman, Adam, Hongbao, Honghao. Yeah, I remember quite a few of you. Anyone want to demonstrate our friendship to help me go through this awkwardness that no one is answering this question?
We were honestly not sure about these questions.
But that's okay, right? Because as I mentioned,
Yeah, because
so what
all
are
of us
the,
are
okay,
guests.
just tell me everything you think that might be helpful to solve this question, and then we can put together.
Okay, so I think so you could like use the diagram on the previous slide, like put the one first. Put the one, and then
You say the data flow
Since two
dependency
has-
graph.
yeah, since 2 has dependency with 1, so you put an arrow.
Okay, so before that, right? For this sequence of instructions, how many instructions am I going to execute?
3 instructions, I guess. Like depends on the size of the linked list, right?
Right, and what's the linked list size?
3 nodes, so it will be around 6 at 9, I mean.
Why
Because you should
9?
compare it with the while.
No.
Oh,
where's
no.
the loop? How many
while,
instructions are there in the loop?
I'm
It's
sorry.
only in the loop, right?
Oh, yeah, I'm sorry.
So we have a total of 15 instructions that we need to look into,
Yeah.
right? So here's the unrolled instruction.
So
But
also
as you
first
said,
of all,
right?
we should like unroll the loop first, and then we put it to the diagram.
Okay. And
So
how to
one
draw the
connect-
diagram?
So 2 connected with 1 on the next level, I guess.
Right. So we cannot execute both of them, right?
Yeah.
Now, for the next cycle, we have 3 and 4. Can we execute any of them?
I guess we can execute 3, but not 4, because we are only allowed 2 instructions per level, right?
Right. And even though for 4 is depending on 1.
Oh, 2. Oh, wait, not 2?
Well, actually 2, right? So terrible.
Yeah.
Okay. So how about the next cycle?
So you connect 2 with 4 with an
2
arrow.
is 4, but it's not immediately next cycle. That's a cycle after, right? And we can put 6 and 5. Anyone from 6 and 5 can we execute?
Can you explain why is it a cycle after? I'm still confused about that.
Which one?
The 2 and 4.
Because 2 is a memory instruction. And you need 2 cycles to get the result.
Okay. And then 5, I guess we can put 5.
Can we?
Wait.
5
No,
is depending
never
on-
mind. Yeah, we should execute 4 first before we go to 5.
Right. So here's the thing, right? Without and right. So 5 can execute it only after 4 is done, right? And how
Yeah.
about 6?
6. I guess it can only be executed after 5 is done, or
Well,
because
actually, after 5 is not generating anything, right? And we assume the branch predictor is perfect.
I see. So we
So,
can put it on the same level as 5.
okay, right? Well, actually 4, right? Because it's depending on 2,
Oh, okay.
right? Right. Okay. But not at this moment, right? So nothing can be done at this moment, right? Next cycle, we fetch 7 and 8, but 2 are already in execution. But when can we start executing 7?
After 6, right?
After 6, right? So,
Yeah.
Michael, you have raised your hand. Question?
Yeah, I was just wondering, isn't test queue and add queue, aren't they both ALU? So could they actually be like on that same line?
Test queue and add queue. So 4 and 6, you have a good point. The answer is no. So actually, 4 has to be postponed. Well, actually 6 has to be postponed because 6 is a later one, right? So yes, for this one, 6 has to be here and 7 has to be here. So Michael, you got it right. Okay, so Nathaniel, are you okay with that?
Yeah.
Okay, so yes, actually it's going to be worse, right? And so, but given that, when are we able to execute 8?
After we execute, so it will have an arrow from 3, right? Because
Right, it only has an arrow from 3, right?
Yeah.
So actually, whenever the ALU is free, we are able to execute 8. Agree with
Oh,
that?
so like at the same level as 5, 7. Wait, never mind. Because
So for 6, we are now putting into execution, and 5 is branch. And because the issue with is 2, right? So cannot be done here, but 8 could be
At the
executed
next
here
level.
for sure, right?
yeah.
Okay, so 9 and 10, right? Now regarding 9 and 10, when can we start executing 9?
After we executed 7.
After
So,
we
but
execute the 7, which take another 2
since 7 is
cycles.
2 cycles, yeah.
Right,
So we go down 2 levels.
right, this levels, right? And how about for 10?
For 10, we should execute it after 9.
We should execute after 9, right? So if you keep drawing this diagram, you will figure out for the linked list, the utilization of your hardware is really bad because you have a lot of gaps, right? So
Okay.
yeah, I have to update the graph a little bit, as Michael pointed out, but the thing is that it takes a lot more than the array code. So definitely linked list is not a great idea if even with superscalar pipeline with auto order execution. So definitely when you write code, you have to consider both. So before you leave the classroom, several things that I want to mention. So first of all, I will update the slides for the quiz question with the correct answer on it. And second thing is that the assignment due Sunday. And if you have any question, don't forget to use our office hours to ask the TA or me questions. And the last reading quiz that would boost your reading quiz performance would be due next Monday. And the final exam, as we mentioned, is scheduled to have a 24-hour, but any 3-hour slot that you pick. And the reason why we scheduled that to be after 1 p.m. is because I have office hours on Friday morning. So that will be your last chance to ask me any question. And the left 5, I keep forget updating this. The left 5 programming assignment deadline is postponed to September the 4th. Other than that, enjoy the rest of your day. And we do have a lab lecture. You are welcome to join. Other than that, see you next Monday.
Hi, Professor.
Yes, question?
Yeah, I was wondering why the graph that you show the third line is empty, because like you said it is about like take 2 cycles. I'm not really understand why this one takes 2 cycles.
You mean the third line? Why is it
Yeah,
empty? Okay, so at this time, right, if you look at the instruction we have, right, the instructions we have, right, for the third line, so we have 5 and 6, right?
Yeah.
But 5 is depending on 4, and
Okay.
6 is also depending on 2, but the result of 2 is not ready at the cycle.
Let me see. So why we can like put 4 on the third line? We cannot do that?
Because 4 is depending on 2. So you cannot execute 4.
Okay, so so the second instruction takes 2 cycles.
Right. Because the second is a memory instruction, right?
Yeah.
Yeah.
Okay, so it should like have a load and have a store, so it have to take 2 cycles, right?
Right.
Okay, gotcha. Thank you.
All right. Good question. Talk to you later.
Bye.